Okay, so this is another status update for my rover, The Stubborn Pursuit of the Path. I'm gonna have an update and some discussion about next steps, and then a little discussion into networking for rovers, because that's very pertinent to the update that I have. So over the last couple of weeks, it actually hasn't been that long since I last did an update. I think it was five weeks or something. I've been focusing on trying to integrate a camera into my Arduino based rover. I didn't actually really know that this would be possible. I discussed a little bit previously, like some of my attempts to do this, and nothing really panned out, because it seems like really kind of pushing the hardware to the limit, and it's definitely a pain whether it's just possible. I just wanted to see if I can get it to work. So starting off here with the limitations. Again, this build is based around the Arduino Uno, which is just 16 megahertz and not very much RAM at all. You'll notice that the RAM that is available on an Uno is way less than most images you could take with any sort of camera. So whatever I'm doing, I've got to basically stream it straight off of the camera device onto some sort of communication link. You can't really buffer anything. And then I don't have Wi-Fi on this build. I've got this RFM69 transceiver, which is like a packet radio. It can send out a 60-byte packet at a pretty slow speed, and that max of 19.2 is just a way outside what I've been able to accomplish so far. So it's also very dependent on the software that you write. You don't have like a TCP/IP stack on your Arduino unless you write it yourself, or you manage to fit it into the tiny amount of memory you have available. So those are the limitations there. It's also just very expensive from a time perspective to integrate a new piece of hardware like this, since all the software is very custom. It's all in C. I'm getting better at it. I've got some pretty good cool tooling, but it's not like it just connects to a USB device and you've got a little Python script that you can run to pull the image off. It's like everything you do is a little bit harder with the way this is set up. So I wanted to really make sure that I didn't invest too much before I had some idea that this thing was going to work. So I started off with a test harness stage. I showed that a little bit last time, I think, when I was describing my previous attempts. And then moving on to integrating that into the rover itself in the easiest way possible, and then fully trying to integrate a camera into the physical build itself. And a whole along the way, I'm just trying to see if it's going to work at all. Quick digression: I actually started tracking notes for this as a discussion on my GitHub repository, just to kind of see how that would feel. I've done bits and pieces on Twitter for other projects, which is also good, but wow, it's really so much easier just to be able to dump a bunch of stuff into a discussion like this than it is on Twitter. The flip side is no one, I'm sure, has seen this at all. So I'm thinking of trying to figure out how to adapt basically the story that gets told in this discussion into a shorter version in a Twitter thread. I don't know. It was a bit of an experiment. And so step one, my test harness. This was another Arduino I had, an Arduino Nano 33, which is much more powerful than the Uno. But so from my stack of spare parts that I haven't used in a real project yet, I decided to use this one. And all those wires there is all the stuff that's required for this camera. You can read about hardware kind of on the spec sheet or whatever, but to me, it wasn't real until I started really plugging it in and realizing wow, this is a whole lot of wires. How am I possibly going to put this onto my rover that is already full of its own wires? The reason it's so many wires is that this camera uses two buses. It uses the SPI bus and it uses the I2C bus, and then it's got power and ground. I still don't understand why it's got both buses, but I think we discussed that a little bit last time. So my first little experiment here was to just hack up the experiment kind of provided example code they have get it working well enough that I could, their example is to actually dump an image to an SD card. So you have to have like SD card hardware, and then it writes that image out, and then you pull the SD card out, put it in your computer, and you can look at the image. I didn't want to do that. I wanted to try to use the serial console. So I have it dumping at base 64 encoding the image, dumping it to serial, and then parsing the output of the serial with the Python script on my computer so I could decode it. And that really let me kind of get my mind around what this camera was actually going to need to work, both from a hardware perspective and a little bit from the software perspective. I put up some code snippets here, but I don't necessarily expect anyone to really understand it. But I spent so much time trying to understand this example code that they provided. The loops were very strange. I kept having like every time I tried to make a change, I would have like an off by one problem. It was very odd. But I finally got that part to work. It dumped it base 64 out, and then I got a Python script here on the right that just like took the raw data that I had dumped to a file and then parsed it out, and base 64 decoded it out to an image. And that got me my first full correct image out of it. And I was quite excited because every other camera test that I've done has been like, at least something was off. There was like some shifting of colors or something, like something was off. I finally got a clear 320 by 200 pixel image, which is the lowest that you can set this camera to. So with that
question,
yeah.
Since you have a very low data rate, how long did it take you to transmit this image over the radio?
I'm going to get to the radio part in a minute here, but this is over the serial bus, or sorry, over the serial console essentially. And that was pretty fast. Like it was on the order of like 10 seconds to download it over. And this Arduino Nano defaults to the like 115 kilobit or baud rate, 115,000. What is that? It's one of the highest baud rate for the serial console. So it always works really well. Whereas the Uno that I have is like, I don't know if you can crank it up that high. But so for serial, it worked pretty fine. You can like watch the image watch the image data go by. But yeah, getting to over the radio is a different animal. But okay, so integrating this into the Rover build itself, I had everything so nicely put together with my little breakout board here, and then suddenly I need to hack into both the buses that are available on this. So basically I pulled the wires from the radio, put them into a breadboard so that I could connect up two devices to the same bus. And then I was still one pin short. I need a chip select pin so that for an SPI bus, an SPI bus basically needs 4 wires per device. I think that's right, SPI, yeah. I get them mixed up, but they need 2 pins for the communication data, 1 for the clock, and 1 for chip select. And the chip select says like which device is active. So you make the chip select go low, I think, and it says your device can now read on the bus. So it's very versatile that way, but it sure uses a lot of pins. And so I was 1 short. And so what it ended up doing was disabling one of the motors and just using that during this prototype phase. And since I got this, hooked up to the USB cable anyway, it doesn't really matter if the motors work. And then I wrote a little bit more sophisticated software that would integrate into the Rover's operating system, essentially. This is using a lot of my own homegrown CIC framework. Worked pretty well for this. Took a little while for me to kind of sort out how I wanted to handle kind of the delays and asynchronous sort of behavior in a single threaded C program like this. But it worked out pretty well. And I ended up essentially rewriting the example code and the loops to like map better into my head. And then it just became this much shorter, tighter little loop. And I was like, I don't know what they were doing. This is backwards. But this works much better. And then here on the right is where my ground station system is reading the data from the network and writing it out to a JPEG file. And again, you don't necessarily have to be able to read all that. But it almost worked. You can see sort of a horrifying looking image there, which is my Westworld Dr. Ford toy here. So that was my target. You can kind of recognize it. So the question is like, okay, why is this wrong? Am I losing packets? I approached the network piece like, what's the simplest possible thing I can do to dump as much data as possible? And so in my communications system, I have two methods of communication. One of them is request to reply. So when I send a command to my rover, I expect to get a reply back. And that's how I issue commands. And then there's a broadcast mode that's just like, just dump data into onto the radio, and you either get it or you don't get it. And so the simplest thing possible and the fastest is going to be this broadcast mode. So I use that. And when I had it in debug mode, and by debug mode, I mean when I'm running my, I've got it hooked up to the serial port and I can watch my rover working. I'm outputting a bunch of like log events and like all kinds of data so I can see what's going on in the rover. And I didn't really think too much about that, but it turns out at 9600 baud, which is what the Uno is configured to run at, just dumping that serial data out actually slows down the entire loop like pretty significantly, to where like it was dumping all of that in about 30 seconds onto the network in debug mode. And then I turned off debug mode. It dumped everything on the network in like 1 or 2 seconds. Like it was, you could barely see it happening. Unfortunately, what that also meant was the image didn't come through at all. I didn't even get this close. I still had like 50% packet loss. So I was kind of stumped with, or stuck with, well, I've got to do something a little bit more sophisticated. Unfortunately, I was kind of hoping I could just get away with, maybe if I send the image a couple times, eventually it'll come through, but it was pretty much always like pretty twisted like this. So that led me down a little bit of a rabbit hole that also connected back to just like, this is eventually, we're moving towards, if we were to move towards Mars rovers, how do you communicate with them? Because you're not using Wi-Fi. There's a lot of kind of delays that are inherent in sending a packet and wanting to know if it got there. So you've got a whole round trip that has to happen for that. As probably many of you know, TCP/IP is kind of what we all use for this on a daily basis. And it has this concept of a sliding window where it can send a certain number of packets without waiting for a packet to come back to like acknowledge that it received them. And so you can use more of the bandwidth even when you have some latency of the system. But on Mars, well, for all systems, you have the speed of light, I think is your fundamental limit. You're not going to get any better than that. But my system actually has a whole bunch of other delays in it that was making it even worse. So one of them, the first one here, this radio send versus receive mode. The radio is not bidirectional. You set your radio to receive mode or you set your radio to send mode. And when I had migrated from using 2 Arduinos, one for the rover, one for the ground station, this was a very easy thing to manage because they both operate at pretty much the same speed and it just like worked out most of the time. But when I switched to the Raspberry Pi, suddenly that device speed difference and the way the hardware was working was a huge difference. And I had to add essentially an artificial delay that says, when you receive a packet, don't send a reply until your peer has had time to switch their radio back into receive mode. I set that at, I think I originally actually had it like 500 milliseconds because I was still struggling. I've knocked it down to 100 milliseconds. It seems like it's working okay. But 100 milliseconds for a round trip time means that like you're only doing 60 bytes every 100 milliseconds, which is a pretty slow operation. And then I've also got like other, like I've got, like I mentioned, the serial debugging slowed everything down. I think the devices themselves can be slow, and then speed of light is pretty fundamental. But so just like thinking about what that algorithm is going to be to communicate between two devices when you're not just piggybacking on kind of pre-existing stuff, you have to write your own software. I was like, wow, yeah, this is complicated. I'm glad I'm doing this. That got me looking a little bit more deeply into just networks in space. I'm not an expert here, so I'm not gonna. Some of you may know more about this than I do, but it was really awesome. Like you can see on JPL's website, like the current activity of the deep space network. So these are the array of dishes that are here on Earth in 3 different locations, and the different dishes of different sizes for different tasks, and they do handle all the communication for everything is in deep space outside of orbit. This was a few hours ago. It was doing a download for the Lunar Reconnaissance Orbiter, yeah. And you can see there, like the round trip light time is 2.72 seconds. That's not too terrible, but you're not going to have a Zoom call. But I was also kind of curious, like, well, what kind of data rates do you get out of this? They don't really go into that kind of detail, but there's a couple of Twitter feeds that actually do. I think they're using, I guess they must be using the same kind of raw data, and there's a bot that tweets out everything the Deep Space Network is doing, and also the Mars Relay Network, which is has been more interesting because you can see, like, here's the data that's coming from which rover and which path is it using to get back to Earth. And you can also, I hadn't actually seen the Deep Space Network one, which just seems like the more low level, like this is everything the Deep Space Network is doing. And it gives you like a lot of details about like what frequency stuff's running on, and like which dish is being used, which location, all that. So that was kind of cool. But the Mars Relay Network kind of gives me a better intuition about what sort of communication patterns are happening, what's the scale and what's the speeds. And you're really talking about dial-up modem kind of bandwidth from rover to orbiter, and then you've got like a DSL line essentially from the rover to Earth, or from the orbiters to Earth. That's kind of how it seems like it's working out. And then latency obviously ranges from 2 to 20 minutes. This diagram on the right here is another cool visualization that is like live on the web. You can see exactly where the MRO is and what its position is compared to, I think M20. I think those are call signs for the different devices that are on the surface of Mars. So you can see like where it gets close. And can provide that communication relay. And then the rates can actually vary quite a bit based on how far it needs to be able to send it and whether kind of atmospheric conditions are going on. So that's kind of interesting too. So this information is from that engineering curiosity, I think, book, where it has some details about the telecommunications stack, but this is Curiosity, I think. So Curiosity has 2 X-band antennas. One is high gain and one is low gain, and those connect directly to Earth, and so it doesn't use that MRO path. But as you can see, like the data rates are super low compared to what we saw going through the Mars. So this is literally just for like command and like command transmission, I think. So like the high gain has to be pointed directly at where Earth is, and so it has to be very precise. The low gain one is basically used for emergency recovery type scenarios, it sounds like, because since the high gain one needs to be actually pointed at something, the rover has to be operational and doing its job correctly, I think, to be able to communicate with it. So the low gain is like this emergency ability to send any commands to it at all.
Well, what I see very interesting is that you're actually able to call home all the way from Mars.
Yeah, that is pretty interesting. That was completely unexpected to me when I was when I was doing that, because I had been looking at that Twitter feed, I was like, oh, this is how all the communication is done. It's like, oh, there's actually a way to go direct to it. That's pretty impressive.
I'm just thinking, what if we built a Rover that works at these bandwidths?
Mm-hmm. Well, funny enough, I almost have. So, yeah, and then so the UHF antennas can talk to orbiters, and being at a much lower frequency can get are still pretty low bandwidth, but they can do better than just because it's closer, I guess. This is 8 to 128 kilobits per second, but only when an orbiter is nearby, which is not very often. So there's like a window that it does all its communication and data dumps during that time. And then the orbiters seem like they can send the data much faster. I'm not exactly sure how that was done. I didn't find information on that readily available.
But did you calculate what kind of real-time visual feedback you're able to provide?
What do you mean by?
I mean, you have a camera and you have a rover, and you give it instructions that take between 2 and 20 minutes to arrive. And what kind of feedback can the rover give? I mean, just for example, maybe you give a command, takes 20 minutes to get there. The rover carries it out for 15 seconds and sends you back a 15-second clip. I'm just trying to figure out what types of, let's call it quasi-interactive control you can have. And with your stubborn, I mean, you have exactly that. You don't have any local memory, so you can't buffer the images. But if you did.
Yeah, I think it's kind of funny because I have a little bit actually more on this about stubborn itself, but it's kind of interesting in that, like, because stubborn is not, like, the latency is not in minutes, and that's a big qualitative difference in how interactive it can be. But I have so much latency that the bandwidth is really, really bad, simply because my communication protocol is very simplistic. But actually, I'm going to get to that a little bit more in a second. No, we can come back to that. But okay, so we covered a little bit of how the rovers are communicating back to Earth, but I also realized, oh, hey, there's actually multiple vehicles talking to each other on Mars. How are they doing that? And that turns out that's easy to find out. They're using a Zigbee chip, which runs at 900 megahertz. It's actually pretty much exactly what my RFM 69 chips is doing. And it's designed to work at these pretty similar speeds and can communicate like pretty far. One thing that was very interesting, I thought, was that because probably it's got the same trade-offs around, like, if you want to do bidirectional communication, that's way more sophisticated than doing just broadcasting out telemetry data. So when the Ingenuity copter is in flight, it actually can't receive any commands whatsoever. It's just dumping data out of its radio at the highest bandwidth it can. And then once it lands, it can establish a lower bandwidth bidirectional link to like pass commands back and forth, which seems to me very similar to what I end up kind of doing. So coming back to Stubborn and the arducam, what I ended up doing was switching from this broadcast to this request reply, simply because I can't deal with any packet loss with the sophistication that I've got. So I wanted to create something that would, like, just be very precise about making sure all data got there, no matter how long it took. Adding this request to reply from the rover to the ground station. Previously, I was using that pattern only from the ground station to the rover. That seemed to work okay, but as soon as I tried to do both, and I've got I've got basically request replies coming from the ground station to the rover. I've got request replies coming from the rover to the ground station, and I've got broadcast telemetry data all going over the same radio link. I uncovered so many stupid bugs that I had built into my code over time that it seemed like, oh, none of the features are working at all. So that ended up being way harder than I kind of expected, simply because what I thought I had working wasn't actually working yet, because I hadn't really put it through its paces. So that took quite a bit of work to get going. Based on that 100 millisecond delay, that's like the minimum amount where we're going to be able to see. I thought we could probably get about 4.8 kilobits per second out of this, and my test, is less than a quarter of that. So there's a whole bunch of, there must be other stuff going on that's causing extra delays in that request reply cycle that I haven't figured out yet. But considering I got this working earlier today, I don't have any better answers. But there's my image that I got there, and there was. It turns out, yeah, if you don't drop any packets and you have the complete file, it works great. I was briefly worried that like the camera itself, I was getting so many images that were like shifted over a little bit, and I was like, oh, is this something with the camera itself not sending good data? I even had like packet counts and like the packet counts match, what's going on? But just going to request reply and being really sure you got exactly the data that was sent solved all those problems. So that's great. Okay, so I want to actually try to attempt a demo here. And I'm still essentially in breadboard mode. It's running. Oh, actually, I got to plug the battery. I'm going to point this down here at my floor, so you can see the rover's there, but I don't really have a great AV setup for displaying it. What we're going to do is watch it all as if it were running on Mars. We can see on the console here, the uptime is 26 seconds and it's counting up. So my rover is alive. I can send this no op command and I'm getting some communications back. I can take a picture with the snap command. This log data over on the left, that's the log data from my ground station. So it's just kind of dumping out all kinds of diagnostic information about the data that's coming through. And you can see on the telemetry, the size of this camera length is like the buffer essentially on the camera itself. And so you can see that kind of count down as it downloads packet by packet. And of course, because this is a JPEG, the data can really like the size of the image itself can vary a lot depending on what you just took a picture of. Like all my test images were like 3 to 4K because it was like dark and just like a very like zoomed in thing. And then as soon as you take kind of like a longer, more complex photo. Okay, so camera length is 0. And then let's see what we got. So that looks like it's underneath my desk. So I'm going to try to aim this thing. And again, I'm down to just one motor. So yeah, I can only seem to like I can only go one direction too. Let's try this. Yeah, my motor control is not great. So by going just small increments, I'm basically just rotating around in a circle because only one motor's hooked up. It looks like a
So the image data is from the camera to the Arduino It's buffered and sent to the network directly, right?
Yes. So the let's go. No, that's not what I want to do. So in this code, I don't know if you can see this in here, but it says SPI transfer. That's basically how you enable the SPI bus. And it says you could basically send and receive at the same time. It's the same operation. And so it reads a byte from the SPI bus, and then it writes it into my very small camera buffer that's running on the Arduino, passes that to the radio to be sent. And then once we've both sent and got the reply, we can start reading another buffer's worth off the SPI bus.
Oh, okay, thank you.
Where is the JPEG transform done?
JPEG is all done on device. So the camera module itself is pretty intelligent. I think my theory on the reasoning behind the two buses is essentially that there's actually two chips on there that are handling this camera control and camera data transfer and whatnot, and one bus goes for one chip and one bus goes for the other one, because it's got enough smarts to run the camera, and then it's taking that image buffer and transferring, and you can have it encoded as a JPEG, or it also will do video, I think, too. So
okay, and if the image is larger than the packet size, it just gives you raster lines or something like.
No, so I'm basically saying I'm reading it slowly from the camera. So it's got a buffer in its own memory of, okay, it JPEG encoded this 320 by 200 image. It's on its own memory. I'm basically reading it off that camera device 60 bytes at a time and shuffling it through the Arduino.
And how much memory does the camera have on board? Like you said, the Arduino Uno is 2 kilobyte, right? So how much?
Yeah, so the camera must have way more. I'm actually not sure what it is, but it's enough to be able to buffer some video.
Okay. All right.
But so here's my image where I'm rotating around, and we have a very slow exploration of my office here. Okay. So
you have the possibility of defining an area of interest in the image and showing only that part?
I
mean, it's a system capable of being programmed to do that. So I tell him, show me only this part, and it shows it, faster or whatever.
Yeah, I haven't actually dug too deep into the capabilities of this arducam, but I wouldn't be surprised if that was something you could potentially do. That would be very cool, actually. Yeah. Yeah, I should look at that.
Sorry, it's a different question later.
I was just going to say that the arducam is, I believe, the same maker as the what is the Oak D devices to the AI thing. I think they make the cameras for that device too. Yeah,
it's a Luxonis. The name of the company is Luxonis. That's cool. Okay. Yeah. Another question is that where do you think there is a bottleneck here? Is it on the memory? Is it on the network, or is it on memory movements? Because memory movements can be very slow in many cases, basically. And here we can see that there is data moving from the camera to the Pi buffer, to the Arduino buffer, and after to the network stack. So it means it moves at least twice, if I understand well. And each time those can be extremely slow.
Yeah, that's a good question. I don't have great metrics on how long some of these operations take. I had a counter on the, I don't know if how much Arduino programming you do, but I have a standard kind of loop that goes through it's just while one just does this loop. And so my loop, I basically time it and would report that as telemetry data, but you only get the value for the loop that happened right before the telemetry data was sent out. So it's kind of random about what you get.
Okay.
But I've seen them flash through at like 280 milliseconds for the last loop. So whatever happened in that loop, which could be like shuffling data into the radio or reading data off the radio or whatever, took quite a while. I was surprised to see a number that high, but I haven't really got to dig in too deep there. But yeah, there's definitely whatever it is that is happening between receiving a packet and sending it back out, like just that like turnaround time is way longer than it needs to be.
Usually the culprit is a network, especially wireless, but the culprit, the bottleneck. Yeah, memory movement as well. I mean, there is a 2014 paper reviewing memory movement between CPU and GPU when you're doing deep learning. Okay, so sorry, it's slightly different, but deep learning. Every year we've got new GPUs from NVIDIA that are faster, and faster. But that paper shows that the problem is not so much the speed of the GPU, but it's about how many times you're going to swap data between the RAM of the CPU and the RAM of the GPU. And that accounts for more than 90% of the performance of some algorithms, basically. And so memory movement can be surprisingly impactful on the performance. And so because of putting together components that each of them has its own memory, and as we are moving the raw data, even if it's compressed, it's still raw data. Okay, it seems pretty easily to add up on the time it will take.
Yeah, and I wonder too if because these chips are basically connected via a bus that's driven by the Arduino, that it's got to be at a pretty. I wonder if that clock rate, like I didn't do anything to like choose a clock rate that it's set, that's doing these things at, and I wonder how many, like, could I run it faster? If I had a faster Arduino, would that part run faster? That would be interesting to find out.
That's very interesting because Meyer, maybe you have something on that, because Meyer shared with me a few weeks ago. We are trying to collect the data from the spider, okay, from each of the servo, and it's mostly Meyer's work. Okay, so I will give him. But there was a problem that we had a parameter to change. Okay, it was something like a parameter to change to weight, so that on the bus the communication was well aligned, and suddenly the speed was much faster. Meyer, would you have more on this then?
I think you discussed a little bit of that last week, or I guess it was the week before. But yeah, I thought that was interesting that it was all U1. It was such a similar problem to the radio communication problem that I had. Simply that like you have to have enough time for whatever the thing is that's doing both the sending and the listening to like switch its modes to not miss stuff. And the fact that I'm running the transceiver on the ground station is now on the Raspberry Pi, and it's very just, I don't know, it's running on Linux. You never really know when you're going to get around to get to communicate with that piece of hardware again.
Well,
I wonder how much the problem is there.
So what I did was I had 2 transceivers on the ground station, and one only talks and one only listens. So instead of trying to switch it on the line and cut off a packet by mistake, in software you can hear I got all the data, and okay, let's go into the other mode. So I'm not sure it's good for your protocol, but it was good for this protocol.
I have what may be a dumb question. So since Ethernet works on collision detection of packets and just detects when it's garbled and retransmits with that random delay or something, can you replicate that model for these, I guess, simpler onboard buses? Is it because Ethernet is a very heavy stack to run or something? So why can't you do collision detection of packets is my question.
I'll answer that. Ethernet is not a very efficient use of the bandwidth. Okay, if you have synchronized, you can get probably up to 90%, but I understand that Ethernet has difficulty getting even to 30%. I don't remember the numbers exactly, but the numbers are much better if you know when to talk and when to listen. Let's see what Google said.
Got it.
I never thought about that before, but that would make a lot of sense. I do think that there is something to mimicking or doing a homegrown shoddy version of some sort of adaptive data rate that can kind of work with, can adjust itself based on kind of the quality of the radio connection. However, you have to be able to like recover from missed stuff, or if you miss packets, you need to be able to get them back again. And one of my fundamental problems is that I can't buffer it. And basically, if I start sending a packet, and like, I mean, I could probably buffer maybe 2 or 3 packets. Basically, that is the limit on how many that I can send without waiting for kind of confirmation that you got it back again. And then there's probably some queuing theory math there that explains what the kind of maximum you can get out of that is. But yeah, so for what to do next, I could definitely spend a lot of time kind of optimizing this communication stack to get just a little better responsiveness, and kind of, I'd like to understand why I'm like a quarter of kind of what my estimate should be for the bandwidth there. But I need to get a lot more metrics there, and just to figure out like why this is slow. There's quite a few different possibilities, I think. The first thing there was also like just finishing the build. So this is still the breadboard perilously hanging on to the front of my Rover. I'm surprised it didn't fall off. I kind of got it wired on there a little bit, but also the fact that my other motor isn't working, I got to figure out if that's going to be a fundamental problem with trying to stick with the Uno, or because I need that extra pin, or if I have just broken something and that's why it's not working. It seems like I'm also having trouble going backwards, so that makes me think that there's some other hardware problems going on. So those are some of my options. My bottom one here is new hardware. I'm starting to think, all right, I've been very stubborn in sticking with what I've got. Maybe it's time to consider some more options. This is the build that I'm kind of slowly putting together in my brain, based on the hardware that I've kind of ordered over time and accumulated. And that would be having a Raspberry Pi Zero paired with a Arduino Nano. So offloading a lot of the sophistication that I have now in the Rover, written in C, and this pretty complicated, difficult environment, moving some of that intelligence over to the Raspberry Pi, where it'd be much easier to work on, and then simplifying the software that runs on the Arduino, making that much more direct hardware interface and hardware control, as just sort of a more interesting model that might be more flexible. The Arduino Nano 33, which I have is like cheaper than the Uno. It's lighter than the Uno, uses less power than the Uno, runs, was that 4 times runs 4 times as fast and has 100 times as much memory, and has built-in IMU and a few other sensors. So that would be a lot of fun to have those capabilities. And then I found this feather wing is like the form factor for these tiny Arduino hats. I guess they stack on top of each other. But this provides a I2C interface for controlling motors. You do both stepper motors and DC motors. So this would replace my hand-wired, whatever that chip is that I have controlling my motors. That would simplify the wiring quite a bit and free up those pins that I need, and would probably be a lot easier to interface with, I expect. So that's what I'm thinking for a new build. Then I'm still like, well, what is my networking story? Like I kind of like the, it's not exactly low tech, but this alternative to Wi-Fi that makes me really have to dig in and understand kind of latency, and it seems like it's presenting some of the same challenges that one might have to deal with if they had to communicate over extremely long distances. So it's fun to experiment with, but there are more options. So if I have a Raspberry Pi Zero with Wi-Fi on it, I can have at least Wi-Fi on board the Rover, which would have a whole lot of a whole lot of conveniences for sure. I'm considering maybe experimenting with building like a Wi-Fi mesh style network where the Rover is actually joins a mesh of other either Rovers or just like lightweight dedicated devices that I can basically extend a mesh Wi-Fi network to kind of an area that might be interesting for roving. Which actually I'm gonna get to that too a little bit. I can continue with my RFM69, so I could have like a dual stack similar to what we see on like Mars rovers of like, well, you've got this a high bandwidth connection via one path, and you've got this low bandwidth connection that gives you slightly different properties, and you use both when you need to. And that model, I think, is really interesting, but there's also a lot of options for what that lower bandwidth version is going to be. So the RFM69 was kind of a random selection based on price and complexity that I bought off of Adafruit, I think. I didn't really spend that much time looking into it. The other option, Zigbee, as we saw, is what's being used by Ingenuity. That's like a proprietary system, I believe, which is why these chips seem to be really hard to find. Like they're all out of stock everywhere, although it could be supply chain crisis. But I think maybe the proprietary nature of it also makes them more expensive. They seem to be like more like $50 as opposed to $10, I think the RFM69 was. So also this thing called LoRaWAN, that seems very similar to the RFM69, but LoRa is another mesh network that is. It seems like it's a very big thing in the world of Internet of Things. I'm going to get into that a little bit more. And then there's this other thing called Helium, which is also might be fun to think about. So LoRaWAN, it's a mesh network of this kind of like low power but pretty high good distance, where you're basically trying to provide internet service for these low power devices. For I don't know what people are actually using these for, but there's a whole like community of people dealing with trying to create mesh networks. So here's the mesh network that's near me. There's pretty good coverage all over the neighborhood and downtown and whatnot. And like, I don't know what people use this for. It's just like, you don't put your refrigerator on Wi-Fi. Now they can communicate over this other mesh network. This is very low bandwidth types of stuff. So this is like sensor network. Just occasionally sending out a packet that says where it is or something. But it's a space that apparently a lot of people are very excited about. And it's like a whole thing I didn't even know existed. And then, of course, it gets even more sophisticated. There's a blockchain version of LoRaWAN where you mine tokens based on providing LoRaWAN coverage in your area. And then devices can use tokens to pay for their bandwidth needs over this mesh network. And surprisingly, this also allegedly has coverage. I don't know how this works, but that's kind of interesting. You basically buy a router, and that's your mining rig, and then you can kind of like, as long if you and it's you make more money if you're in an area that doesn't have great coverage, or make more. You make money. You make tokens. I don't know. So that'll be interesting to experiment with. I don't know what the hardware requirements are for this kind of thing, but that might be an interesting angle, or at least fun to play with. So that brings me to the end. So many rabbit holes to explore. I'm curious what, if anything in this sort of like networking space and questions about that captures anyone's interest. And then as like kind of a parting thought, I was just like, well, maybe I need to direct my rabbit holes towards actually getting my rover to do something or go somewhere, rove somewhere outside of my garage. And when I'm thinking about networking, it's like, oh, what would actually be a stretch is to go around the block, because my Wi-Fi network isn't going to cover that. But I could probably construct a mesh network on my block that could cover it, or I could probably use some of these other systems, because I actually think there's probably coverage where I live. So anyways, might be interesting stuff to compare to experiment with. I don't think anybody would steal my rover if I was operating that around the block. I don't know.
How is it? What is your block like? In other words, are you able to make an autonomous rover that goes around the block?
I think for my near future steps, it would be more of a telerobotics type operate from my laptop a rover to drive around the block. Although this is probably not a very, shouldn't actually be that hard of a problem from an autonomous
No, I mean, you
perspective.
could put down beacons, for example. It doesn't have to be, pure vision based or whatever. But can your rover actually mechanically survive the trip?
I'm pretty sure this rover can't, although I might be surprised at how far it got. I mean, it's sidewalks, but they're old Seattle sidewalks, so there are sometimes gaps and surprises. I don't know what this would do, actually. I really haven't, but like it's been on a smooth concrete and smooth carpet its entire life. I've never actually tried to run it on like the sidewalk. I wonder how well that would work.
That's the advantage of Wi-Fi, because you can just put a hotspot on your phone and walk behind the rover.
Yeah.
So in terms of a question of what captures your interest, I really like radio as like cheap little radio chips as part of this whole configuration. But I think it would be more interesting to put it in the link between the camera and the rover than between the rover and your sort of control laptop or whatever. And the reason I'm thinking that is I'm thinking of applications like there's no particular reason the camera actually needs to be physically attached to the rover. You can kind of leave a bunch of little cheap cameras with radio chips lying around a place you want to rove, and then your rover goes around sort of polling these stations via radio, collecting the data, and then it comes back within Wi-Fi range and dumps the data onto sort of a more capable network. So something like that becomes possible if you're doing cheap radio, I think, right?
Yeah, so I bought some hardware to start experimenting with, like, can one of these little, I don't even know if are they Arduino based? Are they, I don't, one of these chips that have like Wi-Fi on them, and you can write some basic microcontroller style stuff on there. Thinking I would create a mesh network, but I'm realizing now that they can be so small and so low powered, you could like load a rover up with them and drop them off the back of the rover as you move. It could run a camera and it could watch the rover right away, but it also can provide the mesh connection back to base. That'd be kind of cool.
Yeah, the reason I thought of that is I was wondering like why you're kind of almost being masochistic and like using really low cost and low power components to make like simple tasks hard. And one is just for the fun of it, but I think a more interesting researchy reason is it sort of emulates things you might be forced to do even when you do have resources, like this kind of like polling for sensors. I believe that's the main strategy for underwater autonomous vehicles. So like oceanographic institutes that leave sensors around the ocean floor or like, on buoys out in the ocean, they kind of send out these autonomous vehicles to go poll the data collected over like weeks or months and then come back to the mothership or something like that. So I think this is actually a very interesting design pattern. And there's like reasons other than costs that would force you into this regime.
Right.
And I think it's, definitely an interesting thing to explore.
Yeah, I would be curious from the ingenuity designers, for instance, like that seems like the opportunity to, like they could have thrown Wi-Fi chips on these things. Why did they choose this proprietary-ish? I don't know if it's high cost necessarily what they were using, but is it, I don't know if it's military grade Zigbee or something. But like, why do they use that instead of like a Wi-Fi network for the relatively short distance?
I think
I don't think it's relatively short. I think Ingenuity is flying fairly far from Perseverance. Like some of the flights have been fairly long. It may have gone out of like any Wi-Fi based network that Perseverance could run.
Perhaps.
Yeah.
Zigbee, right?
It was Zigbee, yeah.
Zigbee is more reliable according to the internet.
The main goal of Zigbee is to be low energy first, no? I mean, it was pitched that way when it was created. It was a competitor to Bluetooth back in 2008, I think.
Yeah, I only know of it in the sense of like home automation devices, like light switches and things can run Zigbee.
On battery for a couple of years, right?
Yeah, I guess that's the goal, yeah. But that seems like it's not exactly the design constraints of a helicopter. Like, yeah, it's solar powered and it needs to be efficient, but like compared to the motor, I can't imagine the Wi-Fi stack uses that much power.
I'll share a comparison table. A second. On the channel. So basically, they both have the same range, less power, more reliability.
Yeah, and they said that theirs was designed to work up to 1,000 meters. I wonder how they, but that does put it into kind of perspective. Like maybe it's easier to get Zigbee long range than it is to make Wi-Fi long range.
Maybe it's something prosaic, like maybe the Zigbee circuit is easier to harden against radiation.
Could be.
These were not hardened. As far as I know, they ordered the parts of SparkFun and used non-radar. That was part of like the Ingenuity sort of mission test. Like, can they use non-radiation hardened components? So yeah, I don't know why they did it, but That would be interesting to find out. All right. Okay, so if that's it for this one, I believe you're up next week, Eric.
Yes.
Okay, so you worked it out with Anuraj that you're doing next week. Okay.
Yes, just that I misunderstood last week when I was talking. I misunderstood which week was when. Okay, so it's I can do it next week, basically.
Okay, perfect. So you're on next week. Oh, Mario, you're still
Yes.
recording. You should probably stop the recording now.